Philip Ryan and Jongwoo Kim from the Advanced Photon Source at Argonne, as well as John Liu from the University of Tennessee, who along with Schwa Sanchez all work to integrate the uniaxial stress cells I'll be talking about with the X-ray diffraction capabilities at Argonne. And of course, I'd like to thank all of my funding sources that have made this work possible. So to begin in earnest, our work is broadly motivated by some of the outstanding questions regarding unconventional superconductivity, more specifically, what the role of competing phases and their associated fluctuations have in developing the superconducting state. So it's well known that most unconventional superconductors share a similar phase diagram, whereas the system is tuned via some tuning parameter, a magnetic phase is suppressed, typically ending in a putative quantum critical point, and eventually a superconducting dome emerges, which suggests that the fluctuations associated with this magnetic phase are somehow involved in the superconducting pairing. Now in the iron-based superconductors, there's also the electronic nematic phase, which appears near or simultaneous with the magnetic transition, in which the electronic fluid breaks the C4 rotational symmetry of the underlying lattice. And this nematic phase is also suppressed along with the magnetic phase and ends in its own possible quantum critical point near optimal doping. Furthermore, there are theoretical considerations such as the Monte Carlo results shown here, demonstrating that in principle, nematic fluctuations can lead to an enhancement of superconducting pairing and TC near the nematic quantum critical point. So we have this overall picture in which both nematic and magnetic fluctuations are potentially contributing to the superconducting pairing. So this raises the prospect that if we're able to tune these phases and their associated fluctuations and see how the superconducting state responds, we can gain insight into how all these phases are interconnected. And as it turns out, anisotropic strain is a uniquely powerful tool to couple to these phases. So for example, in the case of nematicity, measurement of anisotropies induced by anisotropic strain, such as elasto-resistivity, are a direct measure of the strength of nematic fluctuations above the ordering temperature. On an even simpler level, symmetry considerations imply that the nematic order parameter is directly proportional to the amount of external strain in the same symmetry channel. So by applying strain, we can enhance nematic order and thus suppress its fluctuations. Furthermore, the strong magnetoelastic coupling in these materials implies that anisotropic strain can also act to tune the antiferromagnetic phase. So for example, work from the group of Pengcheng Dai, who's one of our great organizers, demonstrate that the Nel temperature is increased by uniaxial stress. And even more recently, NMR measurements from Nick Kuro's group directly show that anisotropic strain enhances spin fluctuations above Tn. So with these sorts of ideas in mind, the basic idea of our work is to use anisotropic strain to tune the magnetic and nematic phases and then see how the superconducting state responds. So in order to apply strain to bulk single crystals, we use either commercial or home-built versions of the uniaxial stress device shown schematically here, originally developed by Cliff Hicks. So briefly, the way that this type of device works is that a bar-shaped sample is glued across a gap in a titanium scaffolding, which is attached to 3 piezoelectric stacks. And then by applying voltage to these piezo stacks, we can modulate the size of the gap and thereby apply strain to the sample. Furthermore, by cutting the shape of the sample appropriately, we can control the symmetry type of the strain that we're applying. So the data I'll be showing you has the crystal cut along the 110 direction, which will induce a mostly B2g type symmetry strain, which is the appropriate type for coupling in the ways I described on the previous slide. And lastly, all of this work is in the cobalt-doped barium iron arsenide system, which has the following temperature composition phase diagram. And let me start with an underdoped composition of 4.2%, which exhibits all 3 nematic, antiferromagnetic, and superconducting transitions as the temperature is lowered. So the first set of data I'd like to show you is the effective strain on the resistive signature of the superconducting transition. So you're looking at the resistivity as a function of temperature of the underdoped sample for different amounts of both compressive and tensile strain given by the color bar. So the first thing to notice is that for small values of strain, which are these green curves, the resistivity above the transition changes by a large factor, while the transition temperature itself is relatively unaffected. Now, this is readily understandable due to the presence of nematic domains, which are present because for this composition, the superconducting transition occurs below the structural transition. So for small values of applied stress, the effect is just to align these twin domains while no individual domain experiences any strain. And the large resistivity change we observe can be attributed to the large resistivity anisotropy that's known to exist in the orthorhombic phase. And then for higher values of strain, so that would be the red or blue curves, the crystal is fully detwinned and begins to distort microscopically. And then we observe the superconducting transition to be rapidly suppressed. And this suppression is even more apparent if we plot the resistivity on a logarithmic scale, where we can see that we actually measure a non-zero resistivity down to our base temperature of our system. So quite strikingly, we can seemingly completely suppress the superconducting state with strain. So this sort of broad resistive transition raises the question of how to properly define the boundary of the superconducting state. In particular, we would like to see a bulk thermodynamic signature of this strain-tuned transition. So this motivated us to measure the magnetic susceptibility at fixed temperatures and variable strain, which we did by measuring the mutual inductance of a susceptometer coil pair mounted above the sample on the strain cell. So here I'm showing you the real and imaginary parts of that signal as a function of strain. And here each color corresponds to a different temperature. And these are offset for clarity. So looking first at the real part, at high temperature, there's zero signal for all strain, indicating the sample's in the normal state. And then at lower temperature and low strain, there's a negative diamagnetic signal consistent with a superconducting Meissner screening state. And then by applying either enough tensile or compressive strain, we can suppress that diamagnetism. And then looking at the imaginary part, that suppression comes along with a sharp peak in the imaginary part, marked by these black squares, which is a standard dissipative signature of a superconducting transition. So we can take this sharp feature as a bulk thermodynamic exit out of the superconducting state. And this mirrors what we see in the corresponding resistivity data at fixed temperatures, shown here on a logarithmic scale, where by applying enough strain, we can destroy the zero resistance state. So we can combine this data into a single strain temperature phase diagram, where the green circles mark the rho equals zero boundary, and the black squares mark the Meissner signature. And we see we have this dome-shaped phase boundary with a flat region corresponding to the detwinning region, and then these very steep sloped lines corresponding to the suppression. And this phase diagram also includes this color map, which gives the power of the sample's IV curve at that point. So blue is a value of 1, which gives linear ohmic behavior. And so what we see is that extrapolation of these phase boundaries to zero temperature imply that we can tune a superconductor to metal quantum phase transition as a function of applied strains on the order of 0.5%. So in the underdoped compound, we see that anisotropic strain has a drastic effect on the superconducting state. Now, in the context of thinking about the competing phases, remember that in this composition, the sample has already undergone both nematic and antiferromagnetic transitions. So when we apply B2g strain, we're enhancing both static nematic and magnetic order, and thus suppressing both types of fluctuations. Furthermore, by enhancing the magnetic order, we're presumably increasing the number of carriers gapped by the antiferromagnetic phase. So perhaps it's not so surprising that we see that superconductivity is so drastically affected. But this raises the question of what we'll see in optimally in overdoped compositions without long-range magnetic order, because in this case, we expect B2g strain to actually enhance anisotropic spin fluctuations, while at the same time suppressing nematic fluctuations. So here I'm showing the effect of strain on the superconducting transition for the compositions indicated. So you're looking at resistivity on a logarithmic scale as a function of temperature. And looking first at the optimally doped compositions, which are these top two sets of curves. Remarkably, we see a huge sensitivity of TC for both tensile and compressive strain. And at 1% compressive strain, TC is reduced from 25 Kelvin to almost 5 Kelvin, so a nearly 5-fold reduction. Now, this huge sensitivity is greatly reduced as the doping level is increased. So for the 8.8% composition, TC is much less sensitive. And then for the more overdoped 11.3% sample, it's even less sensitive and no longer symmetric for positive and negative strain. So we can understand this evolution a bit better through some basic symmetry considerations. When we apply uniaxial stress along the 110 direction, we don't just induce the anisotropic B2g strain, but we also induce some amounts of symmetry conserving A1g type strains. And then symmetry then dictates that TC can depend linearly on the A1g strains to lowest order, but only quadratically on B2g. So this evolution from quadratic to linear behavior is a signal of a loss of sensitivity of the superconductivity to the anisotropic strain as we move away from optimal doping. And we can quantify this by normalizing by the zero strain value, fitting a second order polynomial and extracting the coefficient alpha, parametrizing the sensitivity. And we can plot that as a function of doping. And what you see here is that alpha is quite large at optimal doping, so approaching values of 100,000, and indeed shows a strong striking compositional dependence. So the measurements I've shown you so far suggest the following temperature, composition, strain, schematic phase diagram, in which in the underdoped and optimally doped regions near the nematic and magnetic quantum critical points, TC is extremely sensitive to anisotropic strain, enhancing the broken symmetry, and in fact can generate another superconducting dome tuned by strain instead of doping. Now, these findings are interesting for a few different reasons. So one, in the case where superconductivity can be completely destroyed, this provides a platform for studying a superconductor to metal quantum phase transition in a bulk 3D system with strain as a clean in situ tuning parameter. And two, it's a direct demonstration of the importance of the fluctuations of the competing nematic and magnetic phases, because in the same sample, we can use strain to strengthen or weaken those fluctuations and see how the superconducting state responds. So this is what makes the huge sensitivity near optimal doping so intriguing, because as I mentioned, in that case, we are outside the magnetic phase. We expect to be increasing the strength of spin fluctuations, and yet we still see the superconducting state weaken considerably. So perhaps it really is the nematic fluctuations that are important for producing a high TC. So to strengthen this point, let me use my last couple minutes to discuss the Elasto-Hall measurements, where we can directly confirm that we are in fact enhancing spin fluctuations in the optimally doped sample. So to perform these measurements, we use the same uniaxial stress device, still applying stress along the 110 direction, but now we're performing a 5-point measurement, which gives us access to both ρxy and ρxx. So let me begin by just describing the phenomenology of what we observe. So here I'm showing you the Hall resistivity as a function of magnetic field of the optimally doped composition, and this is at a temperature of 27 Kelvin, just above the superconducting transition, for different amounts of both compressive and tensile strain. And we can see that the strain is having an effect modulating the Hall resistivity. And furthermore, the response is fairly linear, allowing us to extract the Hall coefficient, which I'm now plotting here as a function of strain. And what you can see is that the behavior is dominated by a nonlinear response, with both positive and negative strain increasing the magnitude of RH, making it more negative. And strikingly, this effect is quite large. So with 0.5% of strain, we see over 100% change in RH. Now we can also measure this quantity a different way by fixing field and sweeping strain instead, which results in this blue trace. And these two methods agree, and this latter method is much quicker, which allows us to then track the temperature dependence of the behavior, which I'm now showing here. So this is the same type of fixed field variable strain trace of the Hall coefficient as a function of strain, with each color corresponding to a different temperature. And what you see is that this phenomenon is strongly temperature dependent, with the large nonlinearity developing at low temperatures. So we can compare this behavior with the simultaneously measured elastoresistivity, shown here on the bottom. And this also exhibits a strong nonlinear component at low temperature. And by symmetrizing this data about zero strain, we can isolate the change in the average in-plane resistivity, which by symmetry must be proportional to the square of the anisotropic B2g strain. And we can compare this to the normalized change of the Hall coefficient. So what you see here is that both of these isotropic quantities have a response to strain that is dominated by a strongly temperature-dependent nonlinear response to the B2g strain. And notably, the Hall coefficient is actually even more sensitive than the resistivity, if you look at the numbers here. So at first sight, this is quite surprising because the 0th order interpretation of the Hall coefficient is that it's a measure of the carrier density, or equivalently, the Fermi surface volume of the system. And since anisotropic strain is a volume-preserving distortion, although we expect it to change the shape of the Fermi surface, we don't expect it to change its volume, and thus don't expect it to change RH. Now, this is only true as long as we don't induce long-range magnetic order when we apply strain, because that would open a gap and reconstruct the Fermi surface. But we see no evidence that that is occurring. Instead, we just see a smooth evolution down to 0 strain, with no sharp feature indicating a magnetic phase transition. So how can we explain this giant nonlinear change in the Hall coefficient? So it turns out that there are previous theoretical works which actually provide a consistent explanation of our observations. And the upshot of these calculations is that in multiband systems like the iron pnictides, hotspots resulting from interband scattering from spin fluctuations can completely change the character of the minority carriers. So in this case, causing holes to behave like electrons. And this behavior drastically alters the transport coefficients, in particular leading to a large enhancement of the Hall coefficient as a function of increased spin fluctuation strength.
I finished that lecture.
So with these ideas in mind, we see that the large nonlinear Elasto-Hall effect that we observe can be interpreted as a transport signature of strain enhancing stripe type spin fluctuations in this composition. Okay, so that brings me near the end of my time. So let me just summarize and conclude. So I've shown measurements demonstrating the effects of uniaxial stress inducing anisotropic strain, what the effects are on the superconducting state in the cobalt-doped barium iron arsenide system. And the effect turns out to be quite drastic, with strain proving to be an efficient tool for tuning TC. Furthermore, the way that this response varies as a function of composition provides insight into how the competing phases of nematicity and magnetism and their fluctuations relate to superconductivity. So in the underdoped case where we have long-range magnetic order, strain is able to completely destroy the superconductivity, resulting in a putative superconductor to metal quantum phase transition. More surprisingly, in the optimally doped composition, TC is still hugely sensitive to and suppressed by anisotropic strain. And this is particularly interesting in light of the nonlinear Elasto-Hall measurements, which I argued is a unique transport signature of strain enhancing stripe type spin fluctuations. So this may provide importance or evidence for the importance of nematic fluctuations for the high TC. Now I should say that there are many other possibilities here and caveats to that statement. So for example, we are not considering how the elasto-nematic coupling may be varying across the phase diagram, which I believe Matthias will be discussing in the talk directly after this. Additionally, anisotropic strain is expected to enhance the strength of stripe type fluctuations, but perhaps it is isotropic spin fluctuations or other types that are actually important for the superconductivity. In any case, I think our work motivates a more careful study of the effect of strain on the nematic and spin fluctuation spectrum across the phase diagram and how that correlates with the effect of strain on TC. So with that, thank you for your attention, and I'm happy to take any questions.
Thank you, Paul, for the great talk. Any questions from the audience? Oh, so I saw Amalia is already raised.
Yes, I have a question, if possible.
Sure.
Yeah, very good. Well done. This is a very nice piece of work. My question is about the second part of your talk, in particular about the Hall effect. So when you apply strain, you expect that you affect both the longitudinal component of resistivity, but also the transverse component. So how do you, can you say something about the two components of your resistivity tensor?
Yes, so let's see.
Because you compare, I assume, only with longitudinal component, but in Hall effect, you will symmetrize and anti-symmetrize your data. So you will have access to, let's say, a rho YY component.
Oh, I see. Yeah, so It's a little bit, so you're saying rho XX versus rho YY? Those
right,
two
yes.
different, yeah. So the thing is that when we're measuring this the way that we're doing this measurement, we don't have a direct access to rho YY. Although, like, according to the symmetry, we basically, when you're at compressive strain, you're measuring one component of the resistivity. And when you're on the tensile strain side, you're measuring another component. So basically what we can access is we can access this component, which is the average resistivity. So that would be rho XX plus rho YY. And then by anti-symmetrizing this data, we could also access rho XX minus rho YY. So this component exhibits this quadratic increase, which suggests that there's increased scattering in the average resistivity. The anti-symmetric component, which is rho XX minus rho YY, that is basically giving you the nematic susceptibility of the sample. So that's why you have this sort of anti-symmetric linear component. And that basically, here I can show you actually. So that basically looks like this on the right, which basically is consistent with a diverging nematic susceptibility. So I'm not sure if that answered your question.
Well, I just thought it's good to think about when you measure Hall effect, things become more complicated, and yeah, maybe you have more information there you can extract from the data.
Yeah, so the data that we show for the Hall, like this data, for instance, we actually do anti-symmetrize the data. So we measure a positive and negative field and sweep strain, and then we anti-symmetrize that set of data. Yeah.
Okay, and about the Hall effect, so can you extract something about your carrier density by doing a multi-band analysis of your data and to see what happens under strain with the carriers and mobilities?
So yeah, we can in principle do that. Although if these theoretical works are correct, which it seems like our data is consistent with what they're saying, then actually the Hall coefficient is not simply interpretable in terms of a multi-band situation. So actually these results that they derive, they actually represent a failure of the Boltzmann transport. Like it's beyond the multi-band simple formula that this sort of thing, because if you just look at the numbers, this would suggest that the carrier density is changing by a lot. Like even in
a single band model, I assume.
But even in a multi-band system, even in a multi-band situation, this giant change is actually not very easily explainable. Like the numbers don't seem to suggest that you could be able to change the magnitude of this by this amount. So that's kind of what motivated us to look at these sorts of ideas, where they actually directly show that this sort of change can occur.
Okay, well,
Yeah,
it's good.
yeah.
I mean, I assume you do have access to your rho XX and rho XY components. So in principle, you should be able to try to fit simultaneous them and see what you get.
Yeah, that's a very great suggestion. Thank you.
Thank you.
Okay, great. So we have 3 more questions. I guess Pavel is next.
Yes, when you compare TC obtained from Meissner and resistivity in the low strain region, there seems to be that the resistivity transition kicks in quite a bit above the Meissner transition. Does it suggest that, you know, the formation of domains, perhaps the superconductivity at the domain boundaries is occurring at a higher in the bulk without the domain walls? I'm talking about low strain region. You see the
Yeah.
So I'm wondering whether that tells me that the superconductivity between 10 and 8 is due to domain walls or something like that.
Yeah, that's a great question. I'm not sure. So I know that there's previous work shown that the critical currents or the pinning of the vortices actually depends a lot on the domains. So when you detwin the crystal, you actually can get changes in the critical currents, for instance. And so I think that might also help explain this, because you see that the thermodynamic measurement is quite flat, whereas the TC measured by resistivity is actually changing by a little bit here. So I'm not sure. I haven't thought too much about what you just said, but I think that's a very interesting idea. And I think that definitely at least in terms of measuring TC by resistivity, the domains definitely can have an effect. I'm not so sure about the thermodynamic measurement. I think that should be independent of domaines.
But the resistive transition is in zero field, is measured in zero field. So the vortices shouldn't matter there.
Yeah, sorry, I misspoke. I just meant the critical currents
right.
depend on the domains and the density of the domains.
Okay.
Yeah.
Yeah,
thank you.
For most of the superconductors, the Meissner transition is always, in experiments, is always slightly lower than the resistive transitions. You just need a zero resistance path in order to have zero resistance.
Right, but here it's more pronounced when you have twinned sample. That's
right. So yeah, to quantify this, will be an interesting problem. So Johanna, I think you're next.
Thank you, and thank you for a very nice talk. I was just wondering if you've done this in the B2g channel, because I think you can also have A1G strains squared that could couple quadratically to all these orders. I don't think that's actually the case in this system, but it's something to consider. Yeah, okay.
Yes. So yeah, you're definitely correct in that symmetry also allows the square of A1G. So here's the B1G measurement, and the effect is much smaller there, and it's essentially linear. So yeah, you're exactly right that this type of measurement is required to conclusively show that is the case. And yeah, here's the data.
Thank you.
Welcome.
Great. So last question is from Peng Chen.
Yeah, so I was curious on the so you see the very large suppression of TC. So then you said there's no a static order induced. But I mean, does your diffraction experiment show whether the prediction height actually changes? I mean, under sort of the string that you can apply. I mean, I'm trying to understand. I mean, which way you're pushing the phase diagram. I mean, we know in the case of phosphor doping, when we put a C-axis pressure, you actually push it to the anti-ferromagnetic order state. So I was very curious. In this particular case, I mean, I guess you don't know. As the previous, the question asked, right? That you don't know whether the electron or hole is increasing, but what's actually changing when you put the pressure on?
So, so when you apply uniaxial pressure on one side of the strain, you'll be increasing the C lattice, and on the other side, you'll be decreasing it. I think the fact that we see the same effect for both positive and negative strain kind of shows that it's an effect of, it's a coupling to the in-plane orthorhombicity that's causing this change.
Yeah, but the in-plane orthorhombicity, I mean, it's always coupled. But typically people argue that it's due to the hopping of the electron through the prediction, right? I mean, typically it's always argued. I mean, but yeah, I guess you have a good point. I mean, so in both compressor and tensile strain, you see suppression, but it's very curious, yeah.
Yeah, so in terms of which way we're moving the phase diagram, I mean, you can sort of think of it as we're enhancing orthorhombicity. So it's a little bit complicated, yeah.
But that means you're pushing to the left, right?
Yeah, you're pushing to the left. But I'm not sure if there's a direct, yeah, so you're saying that maybe you are inducing antiferromagnetic order. But so at least in the optimally doped composition, we don't see that. But yeah, in the underdoped sample, I mean, there's already static antiferromagnetic order, and
it's clearly enhanced under the.
And we're enhancing that, yeah. So yeah, I think that's a very good question. And what exactly is happening in the optimally doped composition in terms of magnetic order or not magnetic order, and how the magnetic fluctuations are changing? Yeah, that's basically something that we're very interested in understanding.
Okay, thank you. Yeah.
I think Peng Chen, this means that it's your turn to do the neutral measurement
no, but
near the optimal dome.
under this large strain is very difficult. I mean, yeah.
Right, but compression, no, we can still compare and then see if you can see an onset of indifferent error.
Yeah. Okay.
Oh, so Chunbyang has a questions.
I have a very short question. I think I may have missed something, but I found this Hall response to be very intriguing. So I just wonder. So with longitudinal resistivity, you have the elasto resistance, which is very large. With the Hall coefficient, can you define the analog of that quantity?
So the Hall coefficient should not respond to linearly to anisotropic strain, because by symmetry the Hall coefficient is it's an isotropic quantity. So
that's why it's quadratic.
That's why it's quadratic, right?
Thank you. Yeah.
So what you could define as this quadratic coefficient, but that's something different. So that's kind of why this is so surprising, is that we see this huge change in a quantity that we didn't expect to respond.
Thank you. Yeah. Thank you very much.
Yeah, so this will be the analog of the nonlinear elasticity coefficient. And Johanna has a paper on this.
Yeah, it's very interesting.
Okay, great. So we should move on to the next talk. Thank you, Paul, again. The next talk will be given by Matthias Ikeda from Stanford University. And Matthias is going to talk about very new and powerful measurements, Elastocaloric effect. So Matthias, the floor is all yours.
Can everybody hear me well?
Yes, we can hear you.
Okay. Just 1 second. Great, okay. All right, thank you very much, Junhao, for your introduction. And let me also start by thanking the organizers for putting together this really exciting symposium and for giving me the chance to present my work here today. So today I'd like to talk about nematic quantum criticality in cobalt-doped barium iron arsenide. And we studied this through elastocaloric effect measurements, and therefore I would like to spend the first couple of minutes of this presentation to introduce our AC elastocaloric effect technique and some basics on elastocaloric effect. And I hope that I'll be able to convince you all that this new technique is a really exciting and beautiful technique. We basically used this technique to study all of the results in the main body of this presentation. The main part of the presentation will then focus on our evidence for quantum criticality in cobalt-doped barium iron arsenide. And we find such evidence by studying the strain response of the nematic transition temperature in cobalt-doped barium 1-2. And then the final few minutes of my presentation will then focus on, again, elastocaloric effect measurements. And I would like to show you that elastocaloric effect is able to provide a new thermodynamic probe for the nematic susceptibility. And a couple of take-home messages from my presentation are going to be that AC elastocaloric effect is, as I mentioned before, a quite simple, beautiful, and versatile technique that really calls for widespread application in the field. And then also, as mentioned before, we find evidence for a large regime in the phase diagram for cobalt-doped barium iron arsenide that is governed by nematic quantum critical fluctuations. And then finally, through our elastocaloric effect measurements in the B2g strain channel, we find that the nematoelastic coupling decreases, but the coupling of the nematic degrees of freedom and the charge carriers increase drastically as we increase the cobalt concentration coming from the underdoped side. Before I start my presentation, let me also take a brief moment for acknowledgments. So all the work I present here today was done in Ian Fisher's group at Stanford University, and all the wonderful people I had the pleasure to work with are listed right below here. And out of all these people, I particularly want to point out Kanapat Varasaran, with whom I had the pleasure to work with for many, many years in Ian's laboratory, and I collaborated with him very closely on the quantum critical project I present here today. And of course, I also would like to acknowledge the theory support we got for the work presented here today. And here I would like to mention Steve Kivelson and then Jörg Schmalian and Rafael Fernandez as well. And finally, of course, also our financial support from the Gordon and Betty Moore Foundation, as well as from the US Department of Energy. All right, and with this, I would like to dive into my presentation. And as mentioned before, first, I'd like to talk about AC Elastocaloric effect, or Elastocaloric effect in general. And so Elastocaloric effect really is describes any microscopic mechanism that changes entropy with strain, with applied strain. And really, we are therefore looking for any mechanism that shows a ds, the epsilon at constant temperature that's different from zero. One really prominent example is natural rubber. And in natural rubber, there is polymer chains that can align or that will align under tensile strain. And so it's very clear that this reduces the entropy, as shown here in the middle panel. And so we have here a ds, the epsilon at constant temperature that's smaller than zero. Now, if we were to apply tensile strain really quickly, such that no heat can flow into the rubber band or out of the rubber band, then we are in so-called adiabatic conditions. And under adiabatic conditions, the entropy cannot change. So what we have to have is a balancing contribution. And this balancing contribution originates from a temperature change. And this temperature change as a response to strain is very closely related to the elastocaloric coefficient at constant temperature. And it is this temperature change as a response to strain that we will measure in our experiments. Now let me also explain why the elastocaloric effect shows a feature and under which circumstances the elastocaloric effect shows a feature around continuous phase transitions. So this is going to be very important because we use the elastocaloric effect to sensitively detect the nematic phase transition as a response to strain. And so in the figure on the left-hand side, I plot the nematic phase transition temperature for 2.5% cobalt-doped barium iron arsenide as a function of strain. And as you can see, the nematic phase transition is strain dependent here. Coming from the disordered phase and going through the phase transition into the ordered phase, of course, we expect an entropy change to occur. And this entropy change must also leave an imprint in the heat capacity over temperature, or in the heat capacity, and that quantity is shown in the figure on the right-hand side. Now, in this particular instance, I have chosen here the sample temperature to be slightly below the phase transition temperature. And so we can now calculate the entropy by just integrating this quantity from 0 up to the sample temperature. And the entropy is going to be corresponding to the colored area here. In this example, if I would now apply tensile strain, then the phase transition would shift to lower temperatures. And therefore, the feature associated with the phase transition and the heat capacity, of course, will also move to lower temperatures, increasing the entropy of the system by the area that's shown in green here. And now an entropy change as a response to strain is, of course, just the essence of elastocaloric effect. And so now we understand why there is elastocaloric effect in the vicinity of continuous phase transitions. Under adiabatic conditions, again, we expect the balancing contribution that's originating from a temperature change. And this balancing contribution is shown as red area here. And rewriting this equation, we find that the elastocaloric temperature change as a response to strain is proportional to the critical part of the heat capacity divided by the full heat capacity, and the proportionality constant is nothing else than the strain dependence of the transition temperature itself. And this is a really exciting result because it tells us that the elastocaloric effect measures a critical contribution of the heat capacity well without actually having to measure it against a very large background stemming from non-critical degrees of freedom. And I would like to mention here as well that it is through our AC elastocaloric effect technique fairly easy to tune the system into an adiabatic state because we apply strain in an oscillating fashion, and we can choose the strain frequency such that we arrive in a regime that doesn't allow heat to flow in and out of the sample. And here I would like to show you really quickly just a comparison of elastocaloric effect, which is shown in red, and heat capacity data, which is shown in blue, just to convince you that indeed both quantities measure the very similar temperature dependence. We can find a feature for the nematic phase transition and a feature for the antiferromagnetic phase transition, here in this case for 2.5% cobalt doped barium 1 to 2. But I would like you to notice that we indeed measure the elastocaloric effect against very small backgrounds, and the sensitivity of this probe is extremely high. And with this, I would like to come to the main part of this presentation, and that's going to be evidence for nematic quantum criticality in cobalt doped barium iron arsenide. The experiments we'll be studying here are uniaxial stress experiments, once again, and we apply uniaxial stress along the tetragonal 1 or O axis, resulting in symmetry conserving strain components and also symmetry breaking strain components. Now, the symmetry conserving strain components coupled to all orders to the biquadratic nematic order parameter, and therefore can tune the phase transition temperature to any order. For B2g strains, the situation is a little different. So let me mention here briefly that B2g strains leave the horizontal and vertical mirror planes intact. And so these symmetry elements can still be broken at the nematic phase transition temperature. And it is for that reason that we still expect a true thermodynamic phase transition to occur even under finite B2g strains. But positive and negative B2g strains have to have the same effect on the nematic transition temperature. And so by symmetry, we know that B2g strains can tune the phase transition temperature only quadratically or to any even order. So it is easy to imagine that from just one uniaxial stress experiment, it is impossible to disentangle the effect of symmetry conserving or symmetry breaking strains on the phase transition temperature. However, we can disentangle the effect of each of these strain components if we compare our uniaxial stress experiment to hydrostatic pressure experiments as well. And so this is what's shown again for 2.5% cobalt doped barium iron arsenide here on this slide. The figure on the right-hand side shows our hydrostatic pressure data, and you can see that both phase transitions, the nematic as well as the antiferromagnetic phase transition, are tuned linearly with applied pressure. On the other hand, for our uniaxial stress experiment, we see a very pronounced nonlinearity. And since the strains that we induce through hydrostatic pressure in this experiment are significantly larger than the strains in our uniaxial stress experiment, we can conclude that the nonlinearity indeed stems from symmetry breaking B2g strain. Now, let me mention at this point that while A1G strains only tune parameters in the effective Hamiltonian, B2g strain introduces new operators, and those operators do not commute with the B2g operators. And so therefore, one could expect that B2g strain should strongly enhance quantum fluctuations. But from this experiment alone, it is of course impossible to say whether quantum or non-quantum effects lead to this strong nonlinear response of the nematic transition temperature. Such evidence can be found by studying this property across the phase diagram of cobalt doped barium iron arsenide. And so the figure on the left-hand side here shows the nematic phase transition temperature as a response to strain for various compositions across the phase diagram. At first sight, it's already clear that as we increase the cobalt concentration going towards the optimal dope regions in the phase diagram, strain becomes more and more a sensitive tuning parameter for the nematic transition. And that is true for the linear response of the transition temperature, as well as also for the nonlinear response. And as a first practical consequence, we find that for the highest dopings studied here, it is possible to tune the nematic transition temperature continuously towards a quantum phase transition, or even through a quantum phase transition with strains that are technically feasible in our laboratory. Let me now take a look or show the linear as well as the nonlinear coefficient of the strain response of the nematic transition temperature as a function of cobalt concentration. As you can see, indeed, both of these coefficients increase drastically as we approach a critical composition as determined from a high magnetic field experiment in the absence of superconductivity. Now, if we were here to approach a quantum critical point, we would expect a particular functional form of these coefficients. And as you can see, however, the data density and error bars do not allow to actually extract this power law from this data. I would like to show you, however, how we were still able to find the power law in this data. And so for that, let me start to explain the way we analyze the data. So in the vicinity of a quantum critical point, very generically, there is only one relevant energy scale that determines the physics in the system. And so the nematic transition temperature, or the transition temperature itself, has to obey a power law. And this power law is written down here, and is in this case for symmetry conserving A1G strains, epsilon A1G, the critical value, minus the strain to the power of theta. So this measures just simply the distance to the quantum critical point. The question really is, how far up in temperature should we expect such a power law to hold? And now the idea is, if we were to increase the cobalt concentration and suppress the transition temperature to lower and lower temperatures at zero strain, then eventually we would arrive in a situation where the power law should even be obeyed at zero strain. And this is what we would like to explore in our data. For that, we divide this equation by the zero strain value, which is nothing else than epsilon A1G critical to the power of theta, and Taylor expand, and we find that this quantity should obey a power law with a critical coefficient of 1 over theta. Or with other words, if we plot this quantity in a log-log plot versus the zero strain transition temperature, we should find a linear regime, and the slope of this line should be determined by 1 over theta. A very similar analysis can, of course, also be done for the symmetry breaking B1G strain components, but in this case, as mentioned before, by symmetry, the strains have to be squared. And then we find a very similar result, namely that the nonlinear coefficient should also be obeying the same kind of power law that's governed by the same critical coefficient 1 over theta, resulting in the log-log plot for the nonlinear coefficient, again for a linear function with the same slope. And if we now take a look at our data, we can see that for all the materials showing a transition temperature at zero strain lower than about 60 Kelvin, we indeed find such a linear regime in the log-log plot of these two coefficients, the linear and the nonlinear coefficient. And this is a really interesting result. It gets even more interesting when comparing the slopes of these linear functions here. And the slopes are extremely similar. They are actually the same within the experimental error bars. And this is a result that can only be understood if these two strain components, the symmetry conserving, but also the symmetry breaking strain, tunes the system further away or closer to a single quantum critical point. Now, it's important to understand that these are two different symmetry channels that basically provide two completely different tuning parameters, maybe as different as magnetic field and pressure are. And it's really a very striking result to find the same slope here. And we interpret this as evidence for nematic quantum criticality in a wide regime in the phase diagram of cobalt-doped barium iron arsenide. The same data is even more impressive if we now take a look at the transition temperatures itself, and not only at the linear and quadratic coefficient of the nematic phase transition. And we plot this now against a combined tuning parameter that now includes the linear strains, but also the quadratic strains. And we can see that we indeed observe a perfect linear scaling relation for all materials showing cobalt concentration of 4.8% or higher. And with this, I would now like to go to the last part of my presentation. And that's going to be an explanation for why we see, or why we can probe the nematic susceptibility through Elastocaloric effect as well. And in this case, we need to apply uniaxial stress along the tetragonal 110 axis such that we induce a B2g strain component. And B2g strain, as we know, breaks the same symmetry elements as the electronic nematic order parameter at the nematic transition. And so it is for that reason that through elasto-nematic coupling, B2g strain actually induces a nematic order. Now, if we had a way to measure the amount of order introduced and the amount of strain used to induce this order, we'd be able to get a measure for the nematic susceptibility. Now, Elastocaloric effect measures entropy change as a response to strain and therefore should be ideally suited for this task. Now, I will spare you with the mathematics, but it is really straightforward to calculate the elastocaloric coefficient in the B2g strain channel from a lambda free energy expansion around the phase transition. And we find that the elastocaloric effect should now be proportional to dk dt and also to lambda squared, where lambda is the nematoelastic coupling constant, and also to the amount of B2g offset strain we applied. As the temperature dependence is concerned, as long as the nematic susceptibility, and here we see it's the bare nematic susceptibility not renormalized by the lattice. As long as this nematic susceptibility follows Curie-wise temperature dependence, we expect the elastocaloric effect to follow 1 over T minus T star squared. And this is what we observe for parent barium iron arsenide. We can see that we indeed measure elastocaloric effect that is tunable in magnitude, but also the sign can be tuned by the amount of offset strain we apply. And we indeed see a diverging temperature dependence. Now it is possible to extract this coefficient here by taking isotemperature cuts through our data and then just determining the slope as a response to strain. And what we can find is shown in the figure on the right-hand side. We arrive at the black data points, and the red line here are simply a 1 over T minus T star squared fit. So it is obvious from the data that for parent barium iron arsenide, we indeed are in a situation where the nematic susceptibility follows almost perfectly Curie-wise temperature dependence. Now, this is something that is of course known for quite a while, for example, from elastic stiffness measurements that were presented by Anna Böhmer and others, but also from elastoresistivity as well. But nevertheless, elastocaloric effect measurements in the symmetry channel are really exciting new techniques, since we can measure this quantity basically in parallel to elastoresistivity on the same sample as well. And we can find some really interesting and cool new results. And this is what I would like to show you on the next slide. So the elastocaloric effect is proportional to dk dt. For the elastoresistivity, we know that the elastoresistivity should be proportional to the nematic susceptibility, but there's proportionality constants, namely G, which is a coupling constant of nematic degrees of freedom and charge carriers, and also the nematoelastic coupling lambda. And if we now were to compare these two quantities, we find that the elastocaloric effect should be proportional to the temperature derivative of the elastoresistivity only if G and lambda were not temperature dependent or not strongly temperature dependent. And this is what is shown in the figure on the left-hand side for various compositions across the base diagram of cobalt-doped barium 122. So we can see that indeed G and lambda do not exhibit strong temperature dependence in this system. Coming back to the elastocaloric effect, again, we measured as a function of cobalt concentration, and the data is shown here in the figure on the left-hand side. So you can see that the magnitude of the elastocaloric effect indeed drops significantly as we increase the cobalt concentration. And assuming that dk dt is not strongly composition dependent, and such evidence can be or was provided actually through Raman measurements, we already realize that in this system, the nematoelastic coupling constant must drop down significantly as we approach optimal doped regions in the phase diagram. I would also like to point out that the perfect Curie-wise temperature dependence that we observe for low dopings breaks down for dopings above 4% here, or actually 5%. And This doping regime in which we observe strong non-Curie-wise like temperature dependence in a nematic susceptibility agrees really well with the regime in which we found strong quantum fluctuations. Let me now come to the last slide and show the same elastocaloric effect data again in a color plot and compare it to a color plot on elastoresistivity, or in this case, actually the temperature derivative of the elastoresistivity. So this plot is something many of you will have seen before and are very familiar with. So it's very interesting to compare these two data sets and realize first that indeed the elastocaloric effect shows the largest values around parent compound and so small dopings, whereas small values around optimal doped cobalt doped barium 122, but the opposite is the case for elastoresistivity. As I've explained before, if we assume the temperature derivative of the nematic susceptibility to be insensitive to doping, we can now from this data, comparing this data, extract that the nematoelastic coupling drops down by at least a factor of 5 as we approach optimal doped regions. But at the same time, the coupling of the charge carriers and the nematic degrees of freedom increases by an order of magnitude. And let me point out here at the end that this result is also perfectly in line with a recent study on X-ray diffraction and elastoresistivity put forward by Joshua Sanchez and others from Jim Howe's group very recently. And with this, I would like to come to my conclusions and really briefly go through the relevance of our findings. So as was mentioned before, I would like to re-mention it again. In the absence of the coupling of lattice and nematic degrees of freedom, nematic fluctuations are known from theoretical studies to promote superconductivity. But on the other hand, through theory, we also know that coupling to the lattice actually restricts the critical fluctuations. So what we have found is we have found a wide regime governed by quantum critical fluctuations in the system. But we have also found that the coupling of nematic degrees of freedom and the lattice shrinks as we go towards the, or diminishes as we go towards optimal dope regions in the phase diagram. But at the same time, the coupling to the charge carriers increases drastically. And these are all the ingredients needed for nematic fluctuations actually being important for superconductivity. And since I'm out of time, I would now just real quickly leave you with my concluding remarks, and thank you very much for your attention.
Thank you, Matthias, for the beautiful talks. Any questions from the audience? So there's a question from Pablo.
So, so is the transition, is the Curie-wise temperature that you observe in elastocaloric measurements corresponds? Does it correspond to the actual transition, or is it shifted from the actual transition?
So it's again divergence against the bare transition. So it's basically T star, right? So it's not diverging towards TS, but towards the bare transition temperature T star.
And in this case, the difference is due to the finite strain being applied, or can you elaborate on that?
So the difference is again due to the basically to the coupling of the nematoelastic coupling lambda. Basically, this is really what determines the difference between these two temperatures.
Mm-hmm. Thank you.
Any more questions? Jimmy has a questions.
Yeah, Matthias, beautiful talk. I wonder, I was wondering whether I can connect this quantity elasto-caloric effect with something that has been thought about in sort of the general context of quantum criticality, which is a Grunayson ratio.
Yeah.
So if the system were responding to hydrostatic pressure, the Grunayson ratio would, I think this elasto-caloric effect, as far as I can see, is precisely the strain tuning, stress tuning analog of the Grunheisen ratio in the case of hydrostatic pressure tuning?
So thank you very much for this question. It's a really quick question. In fact, you're perfectly right. So the elastocaloric effect is indeed actually nothing else than exactly a Grunheisen ratio. It's basically just a, as we've seen, it's entropy derivative response to strain divided by the entropy derivative with respect to temperature. And these ratios are called Grunheisen ratios. We have thought a little bit about this. It would be really interesting to measure elastocaloric effect at really low temperatures, maybe in a dilution refrigerator. And it would be really interesting because what we would measure is strain-tuned Grunheisen ratios, but we would actually measure, since we apply different strain components, we'd actually measure some of various Grunheisen ratios, namely symmetry conserving and symmetry breaking Grunheisen ratios. And so it'd be really interesting to study whether one of these Grunheisen ratios might diverge at low temperatures.
But presumably it is the B2g Grunheisen ratio which should diverge.
That's correct.
So the statement is that if you get, so I guess my question to you is that if you analyze your data that way, do you see the divergence of a ds over of a dt over d epsilon divided by t versus temperature?
So I think that we should really measure this quantity at lower temperatures in order for us to study a diverging Grunheisen ratio as a response of the non-thermal tuning parameters. I've actually not really looked into that, but you're right that one could do that and one probably should do that, and would be really interesting to do it.
Okay, thank you.
I have a follow-up question, if I may. May I?
Yeah, go ahead. Yes.
Yeah, so I had a similar question. Let me phrase it in another way. So you interpret all this evolution, and especially this giant elastocaloric effect in the parent material as an electronic phenomenon. However, it is known that if you, so there are two parts of this question. One, am I right thinking that the parent material is less of a metal than a doped one? And if so, then I might think that in a less of a metal, in an insulator, essentially, one would expect in a, there is a class of insulators which we recently called Coulomb floppy networks, to which these materials do belong, because the tetrahedral coordination allows for under-constrained positions of some ions. And so in these materials, it is known that there is a lattice structural transition, which is associated with a giant elastostructural effect, elastoentropic effect, if you like. So if, in other words, the second part of my question, would it be then possible for me to think that, in a parent material, it is a lattice contribution that actually is making this giant elastocaloric effect, while as you dope towards more metallic states, the lattice contribution sort of fades away and you have a decrease of it?
Yes, thank you for this question. A very good question. So just to clarify the situation one more time. So what we think we measure in the B2g strain channel actually corresponds to elastocaloric effects that originates really from nematic fluctuations. So it's really nematic fluctuations that cause the elastocaloric effect in the channel. And basically the fits that we apply here corresponding to this formula really originates purely from a derivation from Landau free energy expansion that basically only considers nematic degrees of freedom. So we do not actually consider any other degrees of freedom. We fully neglect the lattice and other degrees of freedom and still arrive at this form of the elastocaloric effect, which describes the theta almost perfectly, right? So So we are fairly convinced that the data we see in the B2g strain channel originates from nematic degrees of freedom and in this case, nematic fluctuations above the phase transition. We repeated these experiments as well for the case where we apply the uniaxial stress along the 1,0,0 direction where we are not sensitive to nematic fluctuations. And in this case, we find that, as I've briefly mentioned before, that the elastocaloric effect is mainly sensitive to critical phenomena. We find features around the phase transition temperatures, but the background contribution from lattice degrees of freedom is extremely small. And that's small across the phase diagram. It's in fact significantly smaller than any of the data that is shown on that plot. So it's very unlikely that any of this data here is dominated by response from the lattice.
So may just to make it clear, so you are saying that this particular strain affects nematic fluctuations and do not affect the orthorhombic lattice fluctuations that would exist in an insulator in the absence of a nematic of a electronic nematicity.
So I guess what I should say is that it is in particular also the temperature dependence of this quantity that, similarly to the elastoresistivity, basically leads us to the conclusion that it is really the nematic fluctuations that determine the response and not fluctuations from the lattice itself.
But experimentally, these are the same, right? I mean, you cannot say that these are the orthorhombic lattice fluctuations that would exist in an insulator would not be probed by the same strain.
So,
and by the way, the temperature dependence would be very similar.
The temperature dependence would not be similar because if
in an insulator, yes.
So it depends. I guess it depends on what the order parameter for the phase transition really is. But if we basically think of the strain to be the primary order parameter for the phase transition, if we probe this by strain itself, then we would expect a flat temperature dependence, not a diverging one, similar to the elastoresistivity as well.
Thank you very much.
I'm happy to maybe later on
yes, maybe we should discuss more on this. Yeah, I thought the lattice parameter changes is the same similar temperature dependence as the. Anyhow, yeah.
Right. So I think we should save this for the open discussions, and thanks Matthias again, and then we should move on.
Thank you very much.
Thank you, Matthias. So next talk will be given by Anna Bomer. She's from Karlsruhe Institute of Technology.
Okay, good morning, good afternoon, good evening. Let me just present. Okay, does this work? Do you see my presentation?
Yes, we can see your presentations and we can hear you well. So you may begin.
All right. So I would also like to start by thanking the organizers for putting together this very nice meeting. It's really great to see you all. While most of this work was done at Karlsruhe Institute of Technology, I actually recently moved to Ruhr University Bochum, where I took up a new position. So just to mention that, my new affiliation. Today I want to talk about two materials and the evolution of nematic fluctuations. One of them is the 1144, calcium potassium arsenic 4, of which we've already heard yesterday, and then the whole doped and extremely whole doped 1-2 systems. This work was not done alone. It actually started while I was still a postdoc with Paul Canfield. On the 1144 system, crystals were grown by William Meyer. Then the second part, the 1-2, is really driven by Paul Wiecki, who's working with me as a postdoc, and all the great people at KIT. We've had great theoretical support from Morten Christensen and Rafael Fernandez and Faye, and some first principles input from Rosaire and Ladislav. It always is interesting and I think encouraging to remind ourselves that with the iron-based materials, we have a lot of free phase space in the material side as well. So once we can play with substitutions, we can actually do many things. And I don't need to remind this community of the typical phase diagram of the 1-2 compounds. We've just seen that with a stripe type magnetic order with a nematic phase with a superconducting dome. That's what we always have in the back of our minds. But let's look at the 1144 materials and how they are special. And this is, really comes up in contrast to the whole dope 1-2s. So when we have a 1-2, we start with an alkali ion on the A side, and to hold up it, we alloy with an alkaline earth, and to hold up it, we alloy with an alkali element. Oops, tongue twister. So there is a mix of these two elements on the A side, and we have a doped 1-2 compound. On the other hand, and that was the discovery in 2016, some of these elements, they don't mix. When there's a size mismatch, they separate in layers. So we have alternating, say, calcium, potassium layers as one example. So this is not an alloy. This is really a 1144 compound. And that has consequences on the symmetry. So now we have two distinct arsenic sites, one's close to calcium and one's close to potassium. That can be seen, for example, in the arsenic NMR spectrum. It also is seen in the structure. So we have a very detailed structural refinement, the height of the one arsenic plane and the other ones, they are distinct from the iron side. So they're shifted out of their symmetric position here. So we lose the central symmetry. We of course still centrosymmetric, but we lose the I for MMM from this one, and we end up with a P for MMM. The 1144 pure is a beautiful superconductor, 35 Kelvin. So this is single crystal data from the Canfield group. But what we are wondering is, can we get magnetic order in 1144? And there have been some hints. They were from Rozier's calculations, actually, when she tried to reproduce pressure data taken and published here, that she did need magnetic fluctuations to get the correct structures. So if we want to know how to get magnetic order out of these magnetic fluctuations, we went back to this analogy. And I show you here a phase diagram of the whole of 1-2. And we are here on the right-hand side. Sorry. So we are here on the right-hand side. By charge count, we are equivalent to the 50-50. If we want to go towards magnetic order, now we need to reverse, we need to electron dope. And we can achieve that by substituting with, say, cobalt or nickel for the iron. So to do that, let me just plot this inverse and put the phase diagram. And what I will talk about today is the nickel substituted calcium, potassium, iron 4, arsenic 4. The phase diagram we found upon nickel substitution indeed shows some magnetic order. What we find is the suppression of superconductivity. One might think half a superconducting dome, maybe, and we find a magnetic phase coming up here. This magnetic phase was identified to be not the stripe type order as what comes to our mind when we think of iron-based materials, but no, it's what's called spin vortex crystal magnetic order. That was also mentioned yesterday. In the iron plane, magnetic moments form this non-collinear pattern. And when you go around an iron plaquette, the orientation winds. So that's where this vorticity comes from and the name. And there's actually two types. And this one with some all-in, all-out structure was where we named it hedgehog type, some visual. This was also later confirmed by neutron diffraction. So now we have a variety of magnetic orders in the iron-based compounds. And to give an overview and some systematics, let's go to some theoretical description. To describe this order, and that was done long ago, we can use two spinetsky waves. One with two equivalent wave vectors and two different order parameters, M1 and M2. To recover the stripe phase, one of these order parameters is set 0, and then we get our stripes. But in the Ginzburg-Landau approach, there's different coupling parameters, and in the phase space of these coupling parameters, we find different magnetic orders as well. There is this spin vortex crystal magnetic order, where the two order parameters are perpendicular to each other. And that's where the non-collinearity comes from. There's another one where they are parallel and of equal size. That's a spin charge density wave, what it's called, or C4 by some experimentalists. But today we are going to talk about this area here. And where does the 1144 structure come in here? If we look at this, the two distinct arsenic sites and the iron plane, I put again the magnetic structure, and now I add the arsenic atoms. They are symmetry inequivalent, they're distinct. So now this provides some sort of field. That field must be aligned along the z-axis and also has some staggered symmetry. So every other iron plaquette, there's a different arsenic site. So it really turns out that this causes a symmetry breaking field that couples bilinearly to the spin vorticity, the cross product of these two magnetic order parameters. And in consequence, I have to change my free energy expansion here. I add another term with this field eta from the symmetry, different symmetry in the 1144 structure. So in the 1144 structure with a finite eta, this spin vortex crystal phase is enlarged because of the coupling. And that's where this relation comes from. And we're wondering what's the effect on the nematic fluctuations of this spin vortex crystal structure and of this additional eta field. There have been some calculations by Morton and Fay, and let me quickly walk you through that. For all the caveats and approximations, I refer you to the archive. So what's plotted here is the calculated nematic susceptibility on a path through that phase diagram as function of a proxy temperature down to a transition. Here, the transition in zero eta field. So we see deep in the spin vortex crystal phase, there is a finite nematic susceptibility. It's increasing and then it's cut off at the transition. It doesn't diverge. And once we add a field eta, it gets suppressed and the transition is washed out. If we are deep in the stripe phase, the eta field has basically no effect or has no effect at all. In this intermediate one, it suppresses the transition. We go from a divergent nematic susceptibility to a non-divergent one. And the ground state changes from stripe to spin vortex crystal. But what we were wondering is what will this look like experimentally? So here's our phase diagram again, and I want to emphasize this is a phase diagram, or this is a large phase diagram. We go from a TC of 35 to fully suppress the magnetic order. There is no orthorhombicity, there is no nematic order, there is no stripe type magnetic order. So here we are fully tetragonal, and we were still wondering what's the nematic susceptibility in this fully tetragonal phase diagram. And we are looking at elastic resistance and elastic modulus measurements. Elastic resistance I don't need to introduce anymore, thanks to the previous two talks. And we opted to measure two different crystals that are mounted perpendicularly to each other on a piezo stack and a pair of crystals for each crystallographic direction. So here I showed sort of the longitudinal and transverse elastoresistance for one specific composition as an example. From this data, you see, well, the coefficients are fairly small. There's this sign change between longitudinal and transverse, another one between the two crystallographic directions. And to obtain the symmetry components of the elastoresistance tensor, the sum, the A1G component, that's basically the sum of the two. And we see because of the sign change that will largely cancel out. While the B1G and B2 components, that's the difference of the two, that's the ones we are going to look at. And again, that was just mentioned in the previous talk, or it was important part of the previous talk, the B2G elastoresistance coefficient is proportional to the B2G nematic susceptibility. That's the one that's related to our stripe order. So when I do this, here for the one example, the B2G and the B1G elastoresistance coefficients related to this different strains, and that's the doping evolution all over the phase diagram. First of all, the B1G doesn't evolve at all. So it does not depend on the composition. It's unaffected by whatever drives this phase diagram. So there's no interactions there that we will not look at this one. On the other hand, the B2g, that's quite interesting. There is a very pronounced evolution of behavior here, different temperature dependencies, different signs. So let's take a look at that. And I will do that first of all by plotting it in a color plot here over the phase diagram. Notice I flipped the phase diagram. So here's the magnetic phase. We see a sign change, but the nematic susceptibility does not change sign. This has to be the proportionality constant. If we compare that to the cobalt barium 122, there's no sign change here, but there's a significant change of magnitude of this elastoresistance coefficient. And the influence of this prefactor was just recently discussed, well, just 10 minutes ago in the talk and these recent papers. So here we have a case, there's not only a magnitude change, there's a real sign change of the proportionality constant. And that's reminiscent of a result in the whole doped 1-2 system. Here there's no elastoresistance data published to date, but there is a resistance anisotropy in strained or stressed samples. And the sign change was found there as well. So that seems to be related. And that comes from microscopic measurements of well, scattering and Fermi surface changes, which was also explained here. So what we also see is that in vicinity to sign change, the temperature dependence becomes rich. So there's a sign change as a function of temperature as well. And that must also be related to this prefactor. But we think that maybe if we go far enough away from that sign change, we can learn something from the temperature dependence of the elastoresistance, which, well, we can learn something about the temperature dependence of the nematic susceptibility from the temperature dependence of the elastoresistance on these extremes compositions. And that's what I've shown here. And as is customary in the field, I tried a Curie-Weiss fit. For the optimum TC sample, the undoped 1144, well, the Curie-Weiss is approximately working, but there's strong deviations, especially at low temperature. For the nickel-doped one, which would correspond to an underdoped 1-2, there's a beautiful Curie-Weiss law. That works very well. So again, this is reminiscent and familiar from what we know of the 1-2 compounds. This optimally whole-doped barium 1-2, it looks very similar to this optimum to C1144, even the way this deviates. While the underdoped 1-2s, they show a very nice Curie-Weiss law down to their transition, same as here. So this is a very, very familiar behavior. But while we still don't really know about this prefactor, we thought we might try a different probe, the bending modulus, where this resistance prefactor does not enter. What we have here is the same equation that Matthias just used. The nematic susceptibility influences the elastic shear modulus. And with this coupling constant, this combination is dimensionless, and it has to be 1 at the transition. At the nematic transition, the shear modulus vanishes. So we have some handle on the units here. What we actually measure is not the shear modulus, but the Young's modulus, which also has some other non-critical elastic constants, and we try to get a handle on that using the first principles calculations input. So let's go to the results. This is the optimum TC samples, the pure 1144. You see a softening of the Young's modulus, which comes from a softening of the shear modulus and a significant hardening below TC. And this is very similar to the 1-2 that corresponds at similar doping level. Very similar temperature dependence. On the other hand, the nickel doped, or what would be an underdoped one with a magnetic transition, I do know what will be the temperature dependence of the Young's modulus if there's a Curie-Weiss-like temperature dependence of the nematic susceptibility, and that's what this red curve shows you, and it works very well. So here again, we have evidence for a Curie-Weiss-like divergence of the nematic susceptibility. There is a very curious, very subtle anomaly at the spin vortex crystal magnetic phase transition here. So what does it mean for the nematic susceptibility? This is estimates for the nematic susceptibility from these data. There's a few parameters here, but the qualitative dependence, temperature dependence doesn't depend significantly on these parameters. So we are very confident about how this looks like. The nematic susceptibility in this one compound, this pure one, increases but saturates, flattens, and then decreases below TC. That looks like a sign of competition, as we are very familiar with already. The nematic susceptibility in our dope 1144 increases in a Curie-Weiss-like manner, but is far from critical. Remember, this has to be 1 at the transition, so we are much below that. Then at the transition, there's this subtle anomaly that almost looks like an inflection point, or it does look, there is an inflection point here. And it's tempting to compare that with our model calculation, where in the case of finite eta field, which we have in these compounds, there is also predicted to be an inflection point of the nematic susceptibility at the transition here. So to make the connection becomes tempting. So let me summarize my first part. Phase diagram of the 1144 and the B2g elastoresistance coefficient here. On the high nickel content side, the magnetic system, we do find finite nematic fluctuations, even though this is all tetragonal and the transition is also to a tetragonal magnetic state. And these fluctuations are far from critical. But they nevertheless have a Curie-Weiss-like temperature dependence. On the other hand, we find evidence for a, let's call it sub-Curie-Weiss-like temperature dependence of the nematic fluctuations. On the optimum TC sample, it's very similar to the Overdoped 1 to 2, the equivalent one. And we think that might be a result of close to the general magnetic orders being close to the transition line between the SBC phase and the stripe type phase. Overall, most striking is here that we have an example where the prefactor of the elastoresistance changes sign in a composition temperature in a phase diagram, and also becomes likely temperature dependent, at least in a part of this phase diagram. So to come to the second part of my talk, which will be a bit shorter, is, well, we want to go to the other direction. What happens if we go more Overdoped? And something is known about this. Frederick Hardy from Karlsruhe published this in very much detail. Here is again the barium potassium 1 to 2. We can hold up to the extreme. We end up with pure potassium iron arsenide. We can go with further, now vertically in the periodic table, so apply chemical pressure to the rubidium and the cesium compound. And if we go in this direction, we see that the Sommerfeld coefficient, the specific heat coefficient, the effective mass or a measure of the correlations goes up quite a bit. So these are very large values. This comes in the region of heavy fermion compounds. The resistance also looks similar to heavy fermion systems. There's a huge triple R, and there's this almost, well, quadratic or power law-like temperature dependence at low temperature here. And there are superconductors around 2 or 3 Kelvin. There has been a recent report about nematicity in these compounds, going from the barium directly to the rubidium one. And what was reported is a flip, a change from a B2g type nematic behavior to a B1g type nematic behavior. So a flip of the nematic directions, measured using, well, deduced from elastoresistance measurements. We wanted to start with the most extreme compound, the cesium 1 to 2 here. And there is another interesting property of this. It has not only a huge Sommerfeld coefficient, it also has a huge Grüneisen ratio of the Sommerfeld coefficient. We just talked about Grüneisen ratios, which is here the in-plane pressure derivative of the Sommerfeld coefficient. And as a consequence, or almost analogous to this, the thermal expansivity, the alpha coefficient here, is huge in the cesium compound. And I can plot not the alpha, the thermal expansion coefficient over temperature here. I can also plot simply the length change. What we see in the cesium 1 to 2, it shrinks a lot on cooling. It shrinks almost twice as much, or more than twice as much as a copper metal, 4 times as much as barium 1 to 2, and very different from a piezo stick. So a sample on a piezo stack would already experience huge amount of isotropic strain, not a huge amount. So we thought it might not be the best idea. And instead we use a raisable strain cell that was also just introduced to compensate for this strain mismatch. By moving the two sample mounts closer together on cooling, which would be these red stars here, we can keep a sample in a strain-free state within the system. We see that the resistance follows the one of a freestanding sample. If we don't do that, we break the sample or change the state dramatically. So once we have a sample, say at low temperature in this state, we can then apply small strain sweeps and measure the elastoresistance. That's what we did again. And here we use an 8 contact configuration to get longitudinal and transverse resistance at the same time, inspired by this work here. And again, the same symmetry decomposition for the coefficients. And here's already a result for the cesium sample. So the longitudinal and transverse elastoresistance for a sample in 100 direction and in 110 direction. And you see differences to our previous systems. There's no more sign changes here. This means that the A1G elastoresistance is dominant. It's huge here in blue. And the B1G and B2g components are rather small, much, much less than the A1G. And what's really well, that was our first result. And secondly, we went to the evolution of this. We go again over this phase diagram from some optimally doped to the pure potassium, rubidium, cesium. In this one, which is still close to some stripe type, to the stripe type order, we see an increase of the B2G elastoresistance, very similar to what we just had. We have small A1G and B1G components. We go further, the A1G component starts to grow, the B1G shrinks, and the B1G shrinks, and there's a finite B2G shrinks, and there's a finite B1G. We go further, and we see this growth of the A1G component, the symmetric one, the inclined symmetric one. The B2G one, that would be our nematic susceptibility, well, doesn't change very much anymore, it's there. And the B1G is finite as well, but does not diverge. There's no Curie-Weiss or power law dependence here. So the A1G component, that compares very well to our Grüneisen ratios, or even in temperature dependent thermal expansivity here. And there's a fundamental reason for that. It is that the resistance in these compounds is strongly dominated by the entropy. And so with the elastoresistance, the A1G coefficient, we actually get a measure of the Grüneisen ratio here. So this brings me to the summary of my second part. In this evolution, we see a growth of the A1G elastoresistance systematically towards the cesium 122, which is related to the enhanced Grüneisen parameter, while the B2G simply diminishes and the B1G component is finite but never diverges. Thank you very much.
Thank you, Anna, for this beautiful talk. Any questions from the audience?
Yes, can I ask a question?
Yes, go ahead.
Okay, Anna, thanks for the very nice talk. I have a question with respect to the first part. So when you talk about the doping, maybe you mentioned that, but I just missed. So in principle, when you dope with nickel, I guess that you're also introducing some extra magnetic moment. Does something is known about it? That whether the nickel is magnetic when you dope it in the 1144, and in that regard, when you did when you refer to theoretical modeling, I guess that did not take into account the fact that nickel is actually introducing another magnetic impurities into that.
Okay, I think there's two components. No, the theoretical modeling did not take that into account. When you talk about magnetic moments, I think the role of nickel in this 114 is just the same as nickel in the 122s, and that was studied quite in detail. It is an impurity. We see an enhanced residual resistance. We see enhanced scattering. It does not...
Yeah, there's no moment on
that. Exactly. There's no magnetic moments there. It's an impurity. It's an impurity in the iron plane, so it's quite significant, but it's there's no magnetic moments extra.
I see. Okay, thank you.
Chimiao is next.
Yeah, and a beautiful talk. So in anticipation of some discussions we'll likely have in the next session about the last part that you talked about, I just want to understand make sure that I understand what you said. So the A1G contribution looks like there's a strong temperature dependence, but your interpretation is that it's in a way a background contribution. Is that a fair
well,
reference?
Depends on what you call background. It's the A1G contribution that dominates. So when I measure a longitudinal elastic resistance, when I measure just one sample, I will see a strong temperature dependent, but it comes from the A1G component.
Yeah, so the A1G component is the increase as the temperature is lowered, is not signifying any nematic tendency towards nematic order.
Correct. Because
it's just that because you know the overall state. For instance, if you look at the resistivity, there's a crossover happening around 50 Kelvin. And if you look at anything else, specific heat is developing. Is that fair understanding of
yes? So this temperature dependence with this in the cesium with this peak or this large enhancement, this we see in basically everything. It's related to this coherence incoherence crossover behavior.
Yeah, it's something that I would see in heavy fermions, for instance.
Exactly, but it's a symmetric effect. It has nothing to do with distortions. It has nothing to do with nematicity.
And from experimental perspective, what's the subtlety in the assignment of the measured quantity to the components of these various components?
Well, there's different experimental challenges. The challenge here is that one component is small, so to get it out accurately, that's not so easy. What you do in practice is you measure two directions and take a difference. And then it depends on misalignments, maybe. That's one challenge. We use a single sample for the two directions. That helps a bit. It doesn't affect the conclusion that the A1G component is dominant. It makes it difficult to get the exact temperature, depends on the exact size of the subdominant contributions.
I'm just maybe I can sort of some theorists. I don't have a way of thinking about the configurations, but I can count. So is there is there a difference in terms of how many independent quantities that when measured that would allows one to either accurately or less accurately extracting doing this decomposition? In other words, does everybody measure the same number of independent physical quantities, or are the different groups measuring different number of independent?
Well, I think you always need to measure two directions to do this. There's different ways to do that, and maybe John Hall can support me here. But in principle, it's always two quantities and the difference of two directions, no?
Yeah, I think the NS measurements for applying strain along two different directions and still seeing a gigantic response is quite convincing. It's a A1G channel. Yeah. Okay. I mean, in principle, there's there's other method as well. I can further corroborate this, but I think so far the data is quite convincing.
Thank you.
Yeah, I think Ming is next, and then Pavel, and then Amalia.
Really good, nice talk. I just have a question about the first part, 1144. I'm just curious, how high in doping can you dope the nickel? Can you say, for example, go all the way to the end, a complete substitution?
No, unfortunately, no. This becomes already hard beyond the 5% nickel. So the 7.5, the crystals already become smaller, and we have not managed any further. We chose the nickel because, well, we get more electrons per 5%.
I see. So for the same story for cobalt, I guess?
Yeah, for cobalt you can dope more, and then you finish around 12%. So
I see.
Unfortunately, we have not managed to go any further.
I see. Other question is you know, in the other type of the underdoped potassium doped barium 122, even in the C4 phase, there's been PDF measurements that shows that locally the crystal is still orthorhombic.
Correct.
Do you know for this material 144, the same story? Or
I don't know about PDF measurements, for example, in this. It's possible that I missed that. Well, since the nematic susceptibility seems to be finite, I don't see why it should not be locally distorted. Yes, then it's a matter of degree.
okay.
Right, Pavel is next.
The divergence of the Green-Eisen ratio is often associated with some quantum criticality. So in the cesium compound, is there anything like that going on anywhere nearby?
That's a really good question, and something which we have been puzzling about together with Ximiao, for example. So yes, this looks like as a function of chemical pressure. We could go towards such a point. The problem is in terms of physical pressure, that's tensile. So that's not something we can experimentally do very well. We don't know if there was an ordered phase nearby and which one that would be. But it's a question we are looking into, and it's an open question, I would say.
So like any magnetism or it's not known so
we haven't
far.
known. We haven't found it. No.
Okay, thank you.
Okay, finally, Amalia.
Thank you, Anna, and congratulations on your new position, first of all. So my question is more technical. So you're using both the piezo stacks and the razor bill cell. So when you use the razor bill cell, that applies extremely large strain, which takes you outside the linear regime and where you can define a nematic susceptibility. So I just wonder, you know, how much strain is applied with the razor bill and what limit you are working in that regime.
Okay, so in all of this talk we stayed in the linear regime. In the razor bill, we need this huge strain range to compensate for this huge thermal expansion. So in the end, there's not much left, at least on the tensile side. In one of the directions, there's not much left because we need it all to compensate for its thermal expansion. So far in the cesium, it doesn't look very nonlinear until it breaks. Which isn't, yeah, okay. Can happen earlier sometimes.
Thank you.
Let me just comment that no, we also do a lot of measurements on the cobalt barium 122, and then it's really strange that it still show a very linear behavior up to a very large anisotropic stream. Any more questions? Okay, if not, then let's thank Anna again.
Thank you.
And yeah, I think we also conclude our morning sessions for today. And we'll see you 8.5 hours from now for the final sessions of the Iron Days Symposium.
Thank you.
All right, congratulations on your new president, guys.
It's official.
It's official, it happened. Well,
while Anna was speaking, so thank you.
Thank you, guys.
Thank you for being here and not.
We're very
yeah,
happy.
you were competing with Anna. You were competing with Joe Biden.
Yeah, right.
Good. Great to see everybody. Hi, Yan. Good.
Okay. So I'm not sure I can make the midnight, 3 in the morning discussion round.